In this unit, we're going to be looking more closely at atoms. What's going on inside an atom? So up to this point, you might have talked about the idea that in chemical reactions, atoms aren't changed, they're merely rearranged. So if an atom is represented as a Lego, the Legos to whom that one is stuck before the reaction is different than at the end of the reaction. But the Legos themselves haven't changed at all. In other words, if a carbon atom is, in this picture, a 2x4 blue Lego, at the end of the reaction, the carbon atom is still a 2x4 blue Lego. It's just stuck to different Legos than it was earlier on. Well, now we need to make a mental transition from the Lego atom idea to look a little more closely at what the atom is, or how we model it. And so we might shift to an atom looking like this, that has a nucleus at the center composed of protons and neutrons, and electrons orbiting that nucleus. And what we'll find is, in this unit, that this model isn't sufficient either. But it's a little more precise. We're looking at a little more closely than when we consider atoms to be Legos. So let's fill in this table. There are three main subatomic particles that we're going to deal with: the proton, the neutron, and the electron. The proton is positively charged, the neutron has no charge, and the electron has a negative charge. In other words, the magnitude of charge that a proton has is equal to the magnitude of charge that an electron has, but the charges are opposite. Protons and neutrons are in the nucleus of the atom, and for now we can think of the electrons as orbiting the nucleus, something like planets orbiting a sun. All of that you might have known already, but perhaps you didn't know about the mass of these subatomic particles. And it turns out that a proton and a neutron have very nearly the same mass, about 1 AMU. Electrons are much, much less massive than protons and neutrons. They essentially have almost no mass. An AMU is the abbreviation for atomic mass unit, which is what we use to measure atoms. In case you're wondering, it takes almost 2,000 electrons to equal the mass of a single proton or neutron.